3.6. Load balancing and reliability contexts. The company didn't notice the problem on the day it began. Everything looked normal on dashboards. Graphs were green, alerts were quiet, users were logging in as usual. But support tickets started to change tone. Not "the site is down." Instead, "sometimes it hangs." "Checkout worked yesterday but not today." It spins for a while, then finally loads. The kind of complaints that are painful because they are true, but hard to reproduce. So the team did something useful. They stopped staring at charts and started watching individual requests move through the system. And then they saw it. 3 identical servers stood behind the application. On paper, they were equals. But the actual traffic pattern looked absurd. One server was drowning in requests. One was moderately busy, one was barely doing anything. No bug, no dramatic hardware failure. Just uneven load, like a restaurant where one waiter serves the entire room while 2 others lean on the counter. Users on the overloaded server suffered. Users who, by luck, landed on other servers thought the system was fast. Same product. Completely different realities. That's when the senior engineer said something quiet. "We don't have a performance problem. We have a fairness problem." They introduced a component that didn't exist before. Not a bigger machine, not another database. A decision maker. From now on, no request would choose a server by coincidence. Every request would first meet the silent coordinator, the load balancer. The balancer didn't ask philosophical questions. It asked practical ones. Who is least busy right now? Who responds quickly? Who looks like they might be in trouble? And then, thousands of times per second, it answered, "Send this one here. Send that one there. That node feels unhealthy. Avoid it." Suddenly, everything felt different. Nothing mystical happened. The team didn't rewrite the application. The hardware stayed the same. But users stopped seeing random slowness. Requests were spread fairly. Then, weeks later, the real test arrived. One server didn't crash. It degraded. It answered, then paused, then answered again, then froze longer. The kind of failure humans detect emotionally, but computers must detect mathematically. The load balancer noticed. It kept performing health checks, like a doctor with a stethoscope. Are you still responsive? Are your responses on time? Can you still be trusted with user traffic? Eventually, the answer was no, and instead of a late-night incident report, a very different thing happened. Traffic quietly flowed around the 6th server. Users kept working, payments cleared, support didn't notice. Hours later, the node was repaired and rejoined service, cautiously, gradually. The system welcomed it back, but only when it proved itself healthy again. Someone on the team asked, "So, why didn't this become an outage?" The senior smiled. Because failure was expected, and traffic had somewhere else to go. At that moment, the team finally understood. Load balancing is not about spreading traffic. It is about protecting users from randomness, from unlucky placement, from one bad node ruining someone's experience. It turns a pile of machines into something that behaves like one thoughtful system, constantly choosing the safest path for every request. And once you see it that way, you realize reliability is not just surviving failures. It is guiding around them. When engineers finally understand why load balancing matters, the next question is almost always the same. Okay, but what actually does this in real systems? The good news is, nothing magical. Just mature tools that automate the behavior we already described. Let's walk through a few. Not to memorize them, but to see how they embody the idea. NGINX, the quiet workhorse. Many teams meet load balancing through NGINX. It usually starts as a simple web server --, but quietly becomes the traffic coordinator in front of everything. NGINX is loved because it is predictable, fast, and extremely stable. You can configure it to distribute traffic fairly, detect slow instances, remove them from rotation, and let them back in only when they recover. You see it everywhere. Startups, big companies, side projects, because it's simple enough to adopt early, but powerful enough to grow with you. If someone says, We're routing traffic through NGINX. What they really mean is we have a single calm place making smart decisions. A proxy, the specialist. A proxy solves the same problem as NGINX, but its personality is different. It is built with one obsession: load balancing at massive scale. Banks use it, telecom companies use it, systems that move millions of requests per second use it. Engineers choose HA proxy when they want deep visibility into traffic behavior, finely tuned failover logic, and performance so optimized that the load balancer itself never becomes the bottleneck. It's not the first tool beginners reach for, but teams that handle mission-critical traffic often migrate to it later. Not because NGINX failed, but because Hey Proxy gives more surgical control over who gets what and when. Cloud load balancers, reliability as a service. Then there's another category entirely: cloud-managed load balancers. On AWS, Azure, and Google Cloud, you don't install the balancer. You rent one that is already fault-tolerant, redundant, and globally distributed. This changes the mental model. Instead of thinking, how do I keep my load balancer alive? You think, how do I plug my system safely into this resilient front door? Cloud providers automatically watch your servers, remove unhealthy ones, add new ones when autoscaling creates them, and route traffic across data centers if needed. You still design your architecture, but much of the failure handling is built in. The key lesson is not the names. It's this: cloud load balancers aren't there to make things fancy. They're there to make traffic steering survive disasters. Kubernetes, load balancing from the inside out. Kubernetes introduces a subtle shift. Instead of saying, we have these servers, let's balance traffic across them. It says, we have workloads. Let's make sure they stay alive and reachable no matter where they land. Kubernetes doesn't just spread traffic. It constantly rearranges where applications run. If one node dies, the workload appears somewhere else. If a pod becomes unhealthy, it is replaced. The system only exposes healthy endpoints to users. From the outside, requests just work. Inside, there's a whole choreography of movement and replacement. Kubernetes isn't only an orchestrator. It is an operating system for distributed traffic. DNS-level balancing, when geography becomes part of reliability. Finally, there is one more layer that surprises people the first time they see it. Balancing that happens not inside your data center, but at the DNS level. Instead of choosing which server inside a region, DNS balancing chooses which region should handle a user at all. If an entire data center becomes unhealthy, traffic can be shifted somewhere else, sometimes across countries, without users ever typing a different address. It's not instant and it has limitations, but used well, it turns the internet itself into part of your reliability strategy. Different tools, different layers, different strengths, but every single one, NGINX, HAPROXY, cloud balancers, Kubernetes, DNS, exists because of the same simple truth: traffic should never depend on luck. Some tools are chosen because they are simple, some because they scale to enormous volumes, some because they reduce operational burden, some because they integrate perfectly with containers. You don't have to master all of them immediately. What matters is recognizing the pattern, detect which paths are healthy, send users there, avoid risky spots automatically, reintroduce capacity gently when it proves stable. Everything else is detail, which you will learn naturally over time. When interviewers ask about load balancing, they are not testing whether you can name tools. They want to hear that you understand the mindset: systems fail, traffic must stay flowing, and architecture, not heroics, protects users. A weak answer usually sounds like, load balancing splits traffic evenly across servers so everything is faster. That is technically correct, but it misses the heart of reliability. A stronger answer sounds more like this: load balancing is how we stop user experience from depending on which server they happen to land on. It distributes traffic, runs health checks, and automatically routes around unhealthy instances, so failures stay invisible to users. Notice the difference that the second answer connects behavior arrow, reason arrow impact on users. Great candidates also show that they see layers at the application level. We can use things like NGINX or HA proxy. In cloud environments, managed load balancers also handle autoscaling and regional routing. And in containerized systems, Kubernetes adds another layer, making sure only healthy pods receive traffic. Not a list, a structured picture. Then they add one more idea that interviewers really like to hear. Load balancing on its own isn't enough unless you combine it with good health checks, redundancy, and sensible failover logic. Otherwise, you're just spreading traffic across machines that may already be in trouble. That shows you understand how pieces connect, not just how they are named. And the best candidates do something subtle. They shift from prevent outages to absorb outages gracefully. For example, we designed our system assuming individual nodes would fail. Our goal wasn't to eliminate failures, it was to make sure users never felt them. That sentence tells an interviewer everything you think in systems, you expect reality, and you design resilience instead of improvising it. Once a team learns to steer traffic, to reroute around unhealthy nodes and keep users safe, something interesting becomes possible. If we can control where traffic goes, maybe deployments don't have to be dangerous anymore. Instead of updating the system while users stand on it, we can build a second copy beside it, test the new version quietly, and only then move traffic over. That idea leads us straight into the next chapter, blue-green deployments, two parallel environments for safety. End of 3.6.